Hey there, and welcome. We're about to tackle a word that sometimes makes people a little nervous: trigonometry. But what if I told you it's not some scary, abstract math concept? What if it's more like a secret code? A code that lets us measure pretty much anything in our world, all by using one simple shape. So let's dive in and crack this thing wide open. Okay, so how exactly does this secret code even work? Well, let's start with a couple of puzzles that honestly seem kind of impossible to solve without some kind of magic. I want you to picture this. You're standing in front of the incredible Qutub Minar in India. It's massive, and you want to know its exact height. But you don't have a giant ladder or a helicopter. You've got nothing. So how in the world do you measure it just standing there on the ground? Or how about this one? You're standing on the bank of a super wide river and you need to know the distance to the other side. You obviously can't just swim across with a tape measure. It seems impossible, right? Well, these aren't magic tricks. The solution to both of these puzzles, and to so many other problems, from building bridges to mapping the stars, it all comes down to one really elegant and powerful idea: trigonometry. You know, the name itself basically gives the whole game away. It comes straight from Greek: tri meaning three, gon meaning sides, and metron for measure. So when you strip it all down, trigonometry is just the study of the relationship between the three sides and the angles of a triangle. That's it. Okay, so if we're going to start measuring the world, we need to get familiar with our toolkit. And that whole toolkit starts with one very, very special shape. The main tool, the star of the show, is the right-angled triangle. This simple shape, the one with that perfect 90-degree corner, is the absolute key to unlocking everything else we're going to talk about. Now, to really use this triangle, we've got to have names for its sides. So the longest side, the one diagonally across from that 90-degree right angle, is always called the hypotenuse. That one's easy. But the other two sides, well, their names actually depend on your point of view. Let's say we're focusing on one of the smaller angles, like this angle A. The side that's directly across from it, we call that the opposite. And the side that's right next to it, that's the adjacent. So we've got our triangle, and we've named all the sides. The next step is to figure out the mathematical relationships between them. And we do that with three main tools called trigonometric ratios. Let me introduce you. First up, we have sine, which you'll usually just see written as sin. The sine of an angle is just a ratio. It's the length of the side opposite that angle divided by the length of the hypotenuse. That's the formula, opposite over hypotenuse. Next in line is cosine, or cos. This one is the ratio of the side adjacent to our angle divided by the hypotenuse. So you can think of cosine as just adjacent over hypotenuse. And finally, we've got tangent, or tan. Tangent is the ratio of the opposite side to the adjacent side. And here's a neat little trick. Tangent is also just the sine of an angle divided by the cosine of that same angle. So these three, sine, cosine, and tangent, they are the absolute building blocks for everything. And here's a cool little piece of trivia for you. The word sine has had a wild journey. It actually started in ancient India as a term meaning half-chord. Then that word traveled into Arabic. Centuries later, it was translated into Latin, but there was a mix-up. A mistranslation turned it into the word sinus, which means a curve or fold. And eventually, that got shortened down to the sign we all use in math class today. How crazy is that? All right, that's enough theory. Let's get our hands dirty and put these ratios to work. We're going to look at a real example to see how knowing just one little piece of information can unlock all of a triangle's other secrets. Okay, check this out. Let's imagine somebody tells us that the tangent of an angle, we'll call it angle A, is 4/3. Now we know that tangent is just opposite divided by adjacent. So what we can do is draw a right-angled triangle and just label the side opposite angle A as 4 and the side adjacent to it as 3. So now we're just missing one side, right? The hypotenuse. To find that, we pull out our old friend, the Pythagorean theorem. A squared plus b squared equals c squared. So we've got 3 squared plus 4 squared, that's 9 plus 16, which is 25. And the square root of 25 is 5. Perfect. So our hypotenuse is 5. Now that we have all three sides, 3, 4, and 5, the rest is a piece of cake. Sine is opposite over hypotenuse, so that's 4/5. And cosine is adjacent over hypotenuse, which is 3/5. See that? Just by knowing one ratio, we figured out the whole triangle. But this all leads to the biggest, most important question of all. Why does any of this work? I mean, how can a tiny triangle we scribble on paper tell us anything about a giant monument or a huge river? Well, the answer is probably the most beautiful and crucial secret in all of trigonometry. So here it is, the big secret. Look at these triangles here. You can see they're all different sizes, right? But what's important is that their angles are exactly the same. We call these similar triangles. And here's where the magic happens. Because their angles are identical, the ratio of their sides will always be constant. The sine of angle A in this little tiny triangle is the exact same number as the sine of angle A in this huge one. Just let that sink in for a second. This quote from our source material says it all perfectly. The ratios, our friends sine, cosine, and tangent, they are properties of the angle itself, not the size of the triangle. That idea, right there, is the fundamental principle that gives trigonometry all of its power. And that is how we solve our puzzles from the beginning. The gigantic triangle formed by you, the ground, and the top of the Qutb Minar, it's mathematically similar to a tiny triangle you can draw on a piece of paper. As long as the angles match, the ratios are the same. By measuring the angle from where you're standing and the distance on the ground, you can use these constant ratios to calculate the height of the real thing. It's not magic at all, it's just math. So let's end with this thought. If this humble, simple right-angled triangle holds the mathematical keys to measuring everything from rivers right here on Earth to the vast distances between planets, what other profound, incredible secrets are just waiting to be discovered in the simple shapes that are all around us every single day?